Hello again, and now that we know how to deal with support conditions for bodies in 3 dimensions, we need to determine what types of equations of equilibrium we need to write. And firstly, we're going to talk about the degrees of freedom of bodies in 3 dimensions. So let's examine a general body in the orthogonal space x, y, and z, and see how this body can move in general if it's free to move. So this body can firstly translate along the x direction, obviously. It can also translate in the vertical direction, in the y direction. And of course, it can translate in the z direction. So it can translate in the 3 orthogonal directions. Now this body can also rotate around the x-axis, and it can rotate around the y-axis. And of course, as you can imagine, it can also rotate around the 3rd axis, around z. So that means that a rigid body in 3 dimensions has in total 6 degrees of freedom. So it can move in 6 different independent ways. 3 translations along x, y, and z, and 3 rotations around x, y, and z. Now remember that for equilibrium we have to satisfy Newton's first law of motion, which states in part that if the resultant force and the resultant moment acting on a rigid body, if both are 0, then the body will remain at rest if it was originally at rest. And that means that in this case, when again the resultant force and resultant moment acting on a rigid body are both 0, then the body will be in equilibrium. Now we have to achieve these conditions, so we have to ensure that the resultant or the forces and moments along x, y, and z are all 0. So therefore we will have to write 6 equations of equilibrium in this case. So that these will be summation of forces on x, summation of forces along y, and summation of forces along z must all equal 0. And also the moments about x and the moments about the y and the moments about the z axes about some point that we choose are all 0. So we have to write 6 equations of equilibrium, as you can see here on the screen. Now we can write this or these equations in a slightly more simplified format if we use the vector notation. And in this case, we will write that summation of the forces 0, and summation of the moments is also 0 about a point that we select. But each of these 2 vectorial equations contain actually the 3 equations that we presented earlier. So in total, there are 6 equations. Now, let's go back to this table that we've seen before and we kept on populating. We're going to complete the table now by filling in the last row that refers to 3-dimensional rigid bodies. So as I mentioned to you, there are 3 translational degrees of freedom as well as 3 rotational degrees of freedom. And for equilibrium, we have to ensure that the body will not move in any of these directions or around them. So therefore we have to write the 6 equations of equilibrium: summation of forces along the 3 axes and summation of moments around the 3 axes about a point that we select. And that means that we can solve for a maximum of 6 unknowns. So this is the table that is completed. It's a very good summary table for equilibrium of particles and rigid bodies in 2 and 3 dimensions. You should make a note of it and refer to it whenever necessary. Now for 3-dimensional equilibrium, I would like to discuss about a few particular cases. And the first case that I would like to point out is when all the forces that act are concurrent at a point. So even if the forces act on a body, the forces intersect all at a single point. So it may look something like this. All the forces intersect at this point. Now, what we need to find out is how many independent equations we can write for each of these specific cases. So in this case, we will write 3 equations of equilibrium. And this is, in fact, I hope you've easily recognized, is the case of a particle in 3D really, where all the forces act on the particle itself. So the particle can only translate, hence the 3 equations of equilibrium. The second case is when all the forces are concurrent with a line. So let's see how this one looks like. I'm going to assume that, just for simplicity, that the line is parallel to the x-axis. And these are the forces whose lines of action intersect that specific line, as you can see. So what is specific in this case is that the moment arms of these forces with respect to the line are 0, so hence these forces cannot rotate around the x-axis. So hence we don't need to sum the moments about the x-axis. So we end up in the end with 5 equations of equilibrium. Now another case is when all the forces are parallel to themselves. So they're all parallel. So let's see how this case might look like. Again, I'm going to consider that all forces, just for simplicity, are parallel to the x-axis in this case. So these would be the forces, as you can see, parallel to x. And therefore, forces that are parallel to an axis cannot rotate about an axis. So therefore, the moment of these forces about x will be 0. These forces are also perpendicular to the y and z axes, so they cannot translate around these axes. So again, the moments, this is something that you should remember, the moment of a force that is either parallel or intersects an axis is 0. So in this case, we write summation of fx equals 0 only, because these forces cannot produce translation along y and z, and summation of moment around y and around z must be 0, and that's it, because these forces cannot rotate around the x-axis. Finally, the last case is forces anywhere. So meaning the forces can act in any direction and, as I said, anywhere. So this is the really the general case, the most general case, and hence in this case we have no choice than to write all the 6 equations and write for all 6 unknowns. Now these cases, especially the first 3 cases, are very important, because if you recognize these in questions or problems that you have to solve, then you can eliminate some equations that you don't need to write. So your problems will be much simpler, fewer equations to solve, so hence easier to determine the final answers. Right, so thank you very much for watching this lecture, and I will see you at the next one.